So let's get started here. All right, so last time we started the chapter 15, which is related to impulse and momentum. And we derived the equation of the impulse and momentum, and we got this equation from the sum of the forces equal to the mass multiplied by the acceleration. And this is a vector equation. And we said that we can have the mass multiplied by dv dt, and this will give us another equation, which is equal to the sum of the forces multiplied by dt will be equal to m dv. And we integrated both sides from t1 to t2, and this side from v1 to v2. And finally, we got the integration T1, T2, sum of the forces dt will be equal to mv2 minus mv1. And this is the general impulse momentum equation. And we said that this term represents the change in the particle momentum, as the momentum is the mass multiplied by the velocity, and this part is called impulse. An impulse is defined as a force over time. It's a force exerted on time. So, for example, if we, for example, have a particle here, and this particle has initial momentum of like this way, and let's assume this momentum is equal to m v1, and it's a vector dimension, has a vector, it has a direction. So, and this particle got some impulse, and this impulse is in this direction, and the impulse is equal to the integration of f dt. So finally, this will give us same particle, and it will have different momentum, different in magnitude and different in direction. So this is how it works. You will have, like if you put this in the other side, you will have mv1, and then you will have an impulse, and this will give you a different momentum. So let's just solve an equation. Let's solve an example. I think the example is here, yeah, right here. We can have it like this. So in this example, says that you have, let's draw this problem. I forget to have the drawing. So it says that you have this side view, and you have like a pulley fixed in this place, and there's a cable, and you have a mass we have mass A here, and there's a mass B here, and the block A has a 10-pound weight. So this block has a weight equal to 10 pounds on a rough surface, while it's connected to a cable and frictionless pulley to 8-pound block B. The system starts at rest, so we know all the velocities are equal to 0. The initial velocity, and reaches velocity 5 meters per second, after 5 seconds reach 1 foot per second. Determine the friction coefficient for block A and the tension in the cable. So given the time and given the velocity and knowing almost all of the forces in the problem, so this is a good problem to be solved by the concept of impulse and momentum. And actually, you can solve this problem as a system, or you can solve this problem as a separate blocks. So you can apply the equation of the impulse and momentum on block B separately from block A, or you can apply it for the whole system. So let's try this together and see how it works. So let's solve block B first. So we know that this system will be moving in this direction. So we will assume this is our positive direction, and here the velocity will be equal, after 5 seconds it will be equal to 1 foot per second. So v2 is equal to 1 foot per second, and it starts from rest, so v1 is equal to 0. So let's apply the impulse and momentum equation. So let's have the impulse and momentum equation here. So we know that mv1 vector plus the integration from t1 to t2 will be equal to f dt, and here we will have mv2. Let's apply this number one for block B. So for block B, here's block B, and here's the forces acting on block B. You will have W, and you will have tension in this cable. So this is the only two forces that we have on block B, and we will assume that the positive direction of the forces in the direction of the movement. You can assume the positive in the other direction like this, but you will have to also assume here that the positive in this direction. So you will have to be consistent because you know the direction of the motion. If you switch them, because it will never happen that this body will go down and this body will go in this way. So knowing this piece of information, you will have to assume a consistent direction of the motion. So you make both of these bodies are moving in the same direction. So let's assume that this is our positive direction, and let's apply this equation, and we will apply this equation in y. So here it will be mv1y equal to, so here this equation is a vector, just like to mention. This is a vector equation, so you will have all of these as a vectors. So this equation can be written as a scalar after you have the components in x and y direction. So it will be something like sum of fx dt will be equal to mv2x minus mv1x. And similarly, you will have it in the y direction, sum of fy dt equal mv2y minus mv1y. So we talked this last time. All right, so we will apply this in the y direction, and we will have mv1 plus the integration of the sum of the forces with respect to t will be equal to mv2y. And we have the mass, so we will have, actually, we can put m, and we know that v1y is equal to 0 because it starts from rest. And the sum of the forces that we have in y direction, we have w, because it's in the positive direction that we assumed, minus t. So we have w 8 pounds, and we don't know t, and all of this integration dt from 0 up to 5 seconds. And this should be equal to the mass of block B, which is 8 over 32.2, multiplied by V2y, and which is given 1 feet per second, and it's in the positive direction as well. And from this, you will have 8 minus t multiplied, after you integrate this, it will be multiplied by 5, and this will be 0. And all of these will be equal to 8 over 32.2, and you will able to get the tension which will be equal 7.95 pound, because this is a US unit problem. So we got the tension, which is the requirement in B. So let's get the friction coefficient, and we know that we can get the friction coefficient from here because this is the only block that has friction force. Because if we put all the forces here, so you will have a normal force, and if this body is moving in this direction, so the friction will be in this direction, and the friction will be equal to mu k multiplied by n. So let's solve a block A to get the friction. Block A. So block A, something like this, and you will have to put all the forces, and we call this the free body diagram. And we will have a friction. Okay, and here's W. So we need to get N so we can calculate the F of friction. So we can get from the sum of F in the Y direction will be equal to MAY. And we know that AY is equal to 0. So the sum of Fy will be equal to, let's assume that the positive Y direction is going up. So we will have N minus W equals 0. So N will be equal to W, which is, I think, 10 pounds. Okay, we got N. Now we are ready to apply the impulse momentum equation in the Y direction. So in the X direction, we have another force coming from the cable this way. So we have tension here. So we have F of friction this way, and we have a tension from the cable in this way. And let's apply the impulse momentum equation. So we will have M, and we will apply this equation in X direction because this is where we have velocity. So we will have V1x plus the integration of the forces dt will be equal to mv2x. So we know that this body is moving 1 feet per second in the X direction, and this is the positive X because all the system is moving 1 feet per second in this direction. And the initial velocity is 0, so it will be m, and here's 0. And let's see what forces that we have. We have in the positive direction, we have the tension in the cable, which we just got it here, 7.95 minus F of friction, which is mu k multiplied by n, which is 10 pounds. And all of this integrated with respect to t from 0 up to 5. And this will be equal m block A, and m block A is 10 pound weight over 32.2 multiplied by V2, which is equal to 1 meter per second. So when you solve this equation, you will have only one unknown, which is mu k, so 7.95 mu k multiplied by 10, and all of these multiplied by, when you integrate this, you will have t, so you will have 5 minus 0, it will be 5, and this will be equal 10 over 32.2. And when you solve this equation, you will get that mu k will be equal to 0.786. So this is how you solve this problem. We divided them into blocks, and we solve each block separately. And actually, you can solve this as a system. And when you solve this as a system, the tension in the cable will not be you will not be able to get the tension in the cable because you will have T in this way and T in this way, so all of them will be cancel each other, or you will solve them like as a one body, so the tension in the cable will not be shown, so you will not be able to get B. So if we were not asking, like if I didn't ask you in the problem about the tension in the cable, this problem will be easier to solve it as a system. So let's see how can we solve this problem as a system, like very, very quick. So we can have a full equation. So this will be our direction. So we will assume this is the positive direction. So we will have mv1, and it's not x and y because it's like a curved direction, plus some of all the forces that we have, F dt, will be equal to mv2. And we know that this system started from the rest, so this will be 0. And let's see what the forces that we have in terms of a system. In terms of a system, in that positive direction, we only have the weight, this weight, and we only have the friction. And all the other forces is not included because W and normal force are perpendicular to the motion direction, and the tension in the cable is already embedded inside the problem. So you have tension here and you have tension here. It cancels, or it's embedded inside the problem. So this is the only two forces that we have, and you have W in the positive direction and you have a friction in the negative direction. So this will be equal to 0 plus 8 pound minus F of friction, which will be mu K, multiplied by N, which is equal to 10. And all of these integrated from 0 to 5 dt will be equal to the mass, and this will be equal to all the mass in in our system. So it will be equal to 10 over 32.2 multiplied by 1 plus and actually we can put the 1, let's leave this in half. So this is mass 1, and mass 2 is 8 over 32.2 multiplied by the V, and the V of the system is 1 meter per second. So we put all the mass here, multiplied by 1 meter per second, and we put all the forces on the system here. And only this weight is only one that contributes to the force that can do motion, because this weight is not the one that can do motion. And finally, you will have 8 minus mu K multiplied by 10, and all of these multiplied by 5 will be equal 10 over 32.2 plus 8 over 32.2 multiplied by 1. And here you will only have mu K as unknown, and it should give you same result. You can try it by yourself and solve it. So you can solve this as a system, and you can solve it as a blocks, but make sure that you are moving in the right direction, because at some point you will need to get the tension. So you might apply this for a system and you discover that you need to get the tension in the cable. So after you do this, you might solve one of these blocks like block B, and you get the tension in the cable. Do you have any question? I know that we only two of us. Do you have any question, Tony, on this problem?
Nope.
Okay. So let's see another application on impulse and momentum, and this will be the conservation of linear momentum. So let's move to chapter 15.1, 15.3, conservation of linear momentum. So for conservation of linear momentum, so let's see how does our equation look like. We have m v1 vector plus the integration from t1 to t2 to all of the forces multiplied, and forces is a vector, multiplied by dt will be equal to m v2. And if we have a system of particles like the problem that we just solved it here, it will be the sum of all the masses, and here the sum of all the forces, and here the sum of all the masses. And that's what we did here. We put all the masses here because we are solving it as a system. So this is our equation. So what if our equation doesn't have impulse, like the impulse is equal to 0? So if the impulse is equal to 0, so this term will be equal to 0, and we finally, I don't know what's going on here. and we'll finally end up with the sum of the masses multiplied by V1 vector will be equal to the sum of the masses multiplied by V2 vector. And how's this that we have impulse momentum and we finally end up with only momentum on the system? Like, for example, if we have a surface like this, and we have two particles like this, like two marbles, and these marbles are approaching each other in this way, and they finally will collide here. Let's make them bigger. And these two will collide to each other. So this particle A, and this is particle B, and particle A will exert, will do impulse on particle B, and this will be equal to the sum of the, let's call it B dt, and the other one will respond to A and will have negative B dt. So both of them will do some action on each other, some impulse on each other. And when you solve this as a system, this impulse will cancel the other impulse, and we will have zero impulse on the system. So the external impulses acting on this system will be equal to zero. So if you separated this two, like this, so this one will have B dt, and this one will have negative B dt. So these two impulses cancel each other, and this equation, which is the conservation of the linear momentum, can be applied on the system. So that means that the momentum before the collision will be equal to the momentum after the collision. And let's see like an example on this. I think I have it here. Yeah. All right. So example. So in this example, it says that this box car has a weight of 15,000 kilograms, is coasting at 1.5 meter per second. So let's simulate this problem here. So mass 1 is equal to 15 million gram, which is 15,000 kilogram, and it's coasting with V1. So here's V1 is equal to 1.5 meter per second on the horizontal track when it encounters a 12,000 kilogram tank car that is coasting at 0.5 meter per second toward it. So it coasts in this way, V1 equal to 0.75 meter per second. Okay. And it's shown in if the cars collide and couple together, determine the speed of both cars just after decoupling. So when these two, like let's go back here. When two particles collide together, so here's what happened. First, this one is far from this one, and at some point they will touch each other for less than a second. So there will be a contact, and this particle is moving this way, and this particle is moving this way, and these two particles are almost the same with the same velocity, like at just like this tiny little moment. And after this moment, there will be a restitution, and each one of these particles will go away from each other. Maybe this one will go this way, and maybe this one will go this way, or both of them depends on the velocity and the mass of each other. Maybe this has a bigger velocity and bigger mass. So when it do collide with this smaller mass particle, So it will give some momentum to the other particle to move this way. However, this one reserved some momentum to go this way. But this velocity here will be decreased and the velocity of this body will be increased. So it depends on the mass and the velocity of each one of these particles. So this is how is the collision look like. So it's first to start like have some coupling together at the same moment, and then there will be a restitution and go away from each other. So here in this problem, it asks us the speed of both cars just after the coupling and the average force between them if the coupling take place of 0.8 second. So let's solve this problem. Okay, so let's have our impulse momentum equation. And if we will solve this as a system, so there will be no impulse. Like if we solve this as a system and these two bodies collide together, there will be an impulse here and both of them will cancel each other, and we are good to apply the impulse momentum equation. Sum of mv1 will be equal to the sum of mv2. So let's put case one, number one, which is the collide and couple together. Okay, for collide and couple together, so both of them, each one has a mass, like the initial condition has different mass and different velocity. So you will have ma, let's assume that this is A and this is B. So we'll have ma va1 plus mb vb1. And after this, when they collide together, at this just instant moment, both of them will have the same velocity when they at the collision time. So this will be equal to ma plus mb, and all of these multiplied by v. At this coupling, both of them will have like v in this way, assuming that this has the bigger velocity and bigger mass, so it will force the whole system to move in the direction of this bigger body. So just also keep alert to the signs. So we will assume that this is the positive direction and each opposite direction will be negative. So let's have the problem. We have 15,000 kilogram multiplied by VA, which is positive 1.5 meter per second, plus MB, which is 12,000, multiplied by VB1, which is negative 0.75 meter per second. And finally, this will give us the MA, which is the 15,000 plus the 12,000 multiplied by V, which we don't know, the velocity of the whole system after the collision. So then you can solve this problem and get the V, and the V will be equal to 0.5 meter per second in this direction. So that means just after the collision with the second, these two bodies will have the same velocity at the collision, and these velocity will be equal to 0.5 meter per second, and it's in the positive direction that we assumed. So right now, he's asking about the average force between them. So when it asks us for, let's put number 2, if the coupling take .8 seconds. All right, so let's have the body A, and let's see what will happen. So body A is like this, and this body is colliding with body B, and this one have a force F acting on body B. So this is A and this is B. And body B will have force negative F acting on body A. And this is our positive direction. We know that these two bodies are moving in this direction. So if we want to get the average collision force between them, we will not be able to do this solving them as a system using this equation. If you want to get the force between them, you will have to solve them as a particle, and the conservation of momentum will not be applied because we have force. So if you solve this, like let's say for body A, which is the box car, and this body A will have M1 VA1 plus the integration of the force dt will be equal to M2 V2. I put the term force because I'm solving each body as a single, so I didn't put the I didn't cancel the F because I'm solving element by element. Okay, so let's see. We have M is equal to 15,000 and VA1 is equal to 1.5. And the force, which we don't know, and it's an average, so we can have it as a constant. So this will be F, and the time is from 0 up to 0.8 second. So this will be multiplied by 0.8 second. And this will be equal to, and actually this should be M1, because we are solving one body. And this will be equal 15,000 multiplied by V2, and we got V2 of two bodies. Both bodies will move as a one body with V equal to 0.5 meter per second. So right now in this we can solve it, and you finally will have the force will be equal to 18.75 kilonewton. Actually, you will get the same answer if you solve body B, like using MP multiplied by VB1 plus the integration of the forces. But actually, I made a mistake here. Do you know it, Tony? What is it?
No.
Okay. So the mistake I did is that I used F as a positive. And actually, it should be, I used the F that the body B, because this is the force that acting on body A. This negative F, and it's in the negative direction. So I should have this as negative. If I'm solving body B, so the force that acting on body B is the force coming from A. So this force will acting on body B. So if I'm solving body B, I will have it positive because this is in the positive direction. If I'm solving body A, so I should have F as a negative because this is the force that acting on body A. And finally, it will give you 18.75. So just like be careful about the direction of the forces and the direction of the velocity, so you can have you can solve your problem right. Did you get it? Like the negative force and the positive force?
Yeah, I see what you're saying.
Okay. That sounds good. So let's move to chapter 15.4, which is related to impact. So chapter 15.4 is related to impact, and here we divide the impacts into two types. The first type of impact is the central impact, and the second type of impacts are the oblique impact. So let's differentiate between these two types of impacts. Okay, yeah, so this, I think, yeah. So this is our two types of impact. This one is a central impact and the second one is oblique impact. So for the central impacts, you will have your two bodies are moving on the same line and collide together, and they have a plane of contact. So when they contact to each other, this will be called a plane of contact, and the line of impact is the one perpendicular to the plane of contact. So this is like a linear impact. And the oblique impact, you have your two bodies are moving with angles like they are moving in the plane. So let's assume that this is a 1D. So like you have a table. You have a table here, and these two marbles are colliding together in 1D. This is also a table, but this table is looking from the top view. So this is a side view, but this is top view. And you are looking on, and these two marbles are coming to each other to collide. And this is the direction of the V's and collide here. And this is the plane of contact. And this is the line of impact. But right now we have another two unknowns in the problems, which is the theta and phi, which is the angles of each one of these two velocities. So let's see the anatomy of this motion. Okay, so this is what happened. You have a particle A, let's follow this figure from A to B to C up to E. So we have particle A moving towards particle B. Both of them have almost the same mass, but VA is way bigger than VB. So at some point, VA will catch, particle A will catch B. So this is before the impact. And at the impact, they will collide to each other and exert impulses on each other. So this is the action impulse. So this is what we call the deformation impulse. So this is called and if these two bodies or these two balls, like if you are hitting two soccer balls to each other or two rubber balls to each other, they will both deform. So there will be some deformation between them. Even if it's a very, very solid body, it might happen some deformation, depends on the amount of impact happen. And we call this phase as a deformation impulse, each one of these bodies acting on each other. So this body A will exert B on B, and B will exert a negative P on A. And it will happen, these two bodies at like a second or less than a second, they will move as a one body. So you will have A and B will be moving with V. And then after like a moment, like a second or two, these two bodies will need to get away from each other. And we call this phase as a restitution impulse. So, the restitution impulse is a little bit less than the deformation impulse. So we call the restitution force R dt, and here's R dt. So each one of these bodies will have reaction on each other, and this reaction is called R. And body A exert positive R on body B, and body B exert negative R on body A. And after this restitution, these two bodies will move away from each other. So you will have VA2 and VB2. And this is what will happen. The body A has a bigger momentum at this phase, and it gives us some momentum to body B. And it will end up with that the VB2 will be much higher than VA. So these two bodies started with VA1 bigger than VB2, and after the deformation impulse and restitution impulse, the VB2 will be higher than the VA2. So let's put these things together in equations and define some new terminologies. So let's analyze this motion. So here, let's apply the principle of impulse and momentum to each one of these particles. So let's start with the central impact. Let's have this central impact. So for central impact, let's have our equation MA VA1 plus MB VB1, because this is the sum of the masses multiplied by V1 will be equal to sum of the masses multiplied by V2. This is the principle of conservation of impulse and momentum. And this will be equal to MA VA2 plus MB VB2. This is if we are solving this as a system. If we are solving this as a system, we will be using this equation. So what will happen if we applied the principle of impulse and momentum to each one of these particles? So let's write here, this is as a system, because as a system, you will have this body and collide with this body, and you will have this having a positive force and negative force. So you will have F dt, and you'll have negative F dt, and both will cancel each other. But if we look at body A, so body A, which is this one, is moving with mv, and there is an external impulse acting on this body, and this is equal to negative F dt. And we call this, we will remove F and put B, because we will use new terminologies, which is deformation force, B dt, just a changing in the symbols. And this will, when we solve this body, it will be MA VA1 plus, but we will put minus because we have negative V, so we'll get this minus outside, minus P dt from T1 to T2 will be equal to MA, because it's only one body. So this is MA, and this is VA, but VA 2. And actually, we will do this until these two bodies are getting together and moving with the same velocity. So we know this is state 1 and this is a state 2. Because this equation is applied to this whole system, and we need to only solve one particle, and we know at the collision time, we know that both two particles are moving with velocity v, so we can remove this and put v. So this is for the first phase, which is the deformation, let's call deformation impulse. And after these two particles move away from each other, like you will have, this is the particle, and the other one will be moving away. We call this phase is the restitution impulse, and both of these bodies, so this body will have a negative R dt on this body, and actually this will be phase 3, and this we can call it V2, like this body will be moving, will have, this is MV1 and this is MV2. And if we apply the impulse and momentum on this equation, we will have, so we will be using this phase and this phase. So we will have from 2 to 3, and this equation is from 1 to 2, from phase 1 to phase 2, and from phase 2 to phase 3. So this will be equal to MA, and V1 will be V plus, and you will have restitution impulse, R dt, from T1 to T2, and this will be equal to MA V2 is the final velocity of the body. And we call this restitution impulse. So this is a deformation impulse, and this is restitution impulse. And we can apply this as well on particle B. And from here, we need to define a new terminology, which is called E. E is the coefficient of restitution. And E is equal to the restitution impulse, so the integration of R dt over the deformation impulse, the integration of B dt. And this coefficient of restitution is always less than 1. It's never be more than 1, because always the restitution will be, it could be 1, might be if it's like a fully pure motion without any losses, so you will have R will be equal to B. And when you solve this problem, after solving these equations, you will get that this coefficient will be equal to V minus, let's put it down there. And actually, let's put the final one. The coefficient of restitution between two bodies will be equal to V of the body A, and this is VA1 minus VB1 over VB2 minus VA2. And here's like you have, oh, sorry, I think this will be more than 1. Should be, I switched the terms. It will be VB2 minus VA2 over VA1 minus VB1. So if you have these two bodies and collide with each other, so you have this is VA1 and this is VB1, and when they collide, and after the motion get done, like after they collide and came together like this, and finally they go away from each other, so we'll have like, here's VA2 and this is VB2. So this is the coefficient of restitution. Sometimes in the problems, you will be asked to get the coefficient of restitution, or you will be given the coefficient of restitutions and get some of the velocities in the problem. So let's see what is the cases of the coefficient of restitution. So E could be one of, like, let's assume that if there is no particle B, like you have a wall here, so this is a ground, and you have a ball, and this ball hit a wall. So this wall will never move, but there is a collision here. So VB is equal to 0. So when VB is equal to 0, so this is a special case. For this special case, E will be equal as, from this equation, VB2 minus VA2 over VA1 minus VB1. So we have VB 1 and 2 is equal to 0, and this will give us negative VA2 over VA1. And actually, it will give you a positive quantity because this is the positive direction, which is the direction of VA1. And when this will come back after the collision, it will come this way in the negative direction. And this negative will cancel this negative, and you will have a positive quantity. So this is one special case. And the other cases, like sometimes E could be equal to 1. So if B is equal to 1, that means that our system is perfectly elastic, which means that you have the VA is equal to the VB. So this is, we call it as a perfectly elastic motion or system. And E is equal to 0, that means that your system is fully or pure plastic or inelastic. So that means that there is no restitution. Like when your bodies collide, they will stop. there is no any restitution. So because we have E is equal to the integration of R dt over P dt, so the restitution will be if this is equal to 0, so this part will be equal to 0. So this we call it inelastic or plastic motion or system. So this is how the two systems look like. So let's solve a quick example on the impact. Let's assume that we have a bar like this, and this bar is fixed from both sides, and you have two bodies like a body here that has a groove that allows a motion, and the mass, this is body A and this is body B, and the mass of A is equal to 4 kilograms, and the VA, this is moving in this direction and this move in this direction, VA is equal to 10 meters per second. And here's MB is equal to 4 kilograms as well, and VB is equal to 5 meters per second. So let's solve the system when it's perfectly plastic, like number 1, when E is equal to 0, perfect plastic system. And this will give us this, if you have E here, and you say that this is equal to 0, and you will have VB2 minus VA2 over VA1 minus VB1. So that means that this part is equal to 0. VB2 minus VA2 is equal to 0. That means that VB2 minus VA2, VB2 will be equal to VE2, which is equal to V. So both of these particles after the collision will be one body. They will not leave each other. So this is what the plastic system means. So what we use, that there is a restitution that allows these bodies to move away from each other. But here, the restitution is 0, which means that both bodies will have the same velocity. And from this, we can apply the principle of impulse, conservation of impulse and momentum. So we'll have MA1 VA1 plus MB1 VB1. So this has come from summation of M V1 will be equal to sum of the M V2. And we get the sum of these things, and this will be equal to the two masses MA, and actually this should be MA, just MA, plus MB multiplied by V, because both of these particles will have the same velocity. So here we have MA is equal to 4, V is 10, plus 4 multiplied by 5 will be equal to 4 plus 4 multiplied by V, and then we can get V. So the velocity of these two particles will be equal to 2.5 meters per second. And I assume this is the positive direction. So this 10 meters per second will give much more momentum to the system to move in this way as a two particles with velocity equal 2.5 meters per second. So let's see another case where if we have the system is not plastic and it's not fully elastic, so E is equal to 0.8. So if E is equal to 0.8, you will have this 0.8 will be equal to VB2 minus VA2, and we have here VA1 minus B1, and we have them 10 minus 5. So we can get an equation between the velocities at 2, VB2 minus VA2 will be equal to 0.8 multiplied by 5. So this is one equation. So let's get the second equation from the conservation of impulse and momentum by applying this equation again. So you will have 4, and right now both of particles will not have the same velocity. Each one will have different velocity because E is not equal to 0. E is equal to 0.8. That means there is a restitution, and when these bodies collide with each other, they will go to the second phase when they go away from each other. Maybe this one goes this way and this one goes this way. So let's apply this equation, which has, it will be a little bit different from this one. So it will be MA VA1 plus MB VB1 will be equal to MA VA2 plus MB VB2. So right now we need to divide them because this is not a plastic system. So we'll have 4 multiplied by 10 plus 4 multiplied by 5 will be equal to 4 multiplied by VA2, which we don't know, plus MB, which is 4 multiplied by VB2. And this should give you two equations in VB2 and VA2. And when you solve these equations, you will have that VA2 will be equal to negative 3.5 meter per second, and VB2 will be equal to 8.5 meter per second. Try to change this E and see how this affects the motion of two bodies. So after the collision, A will go this way and B will go this way. A will go this way with 3.5 meter per second. So it was going 10 and now reversed the direction. And here this goes 5 in this direction. Now it reversed the direction with 8.5 meter per second. So this is how the impact problem works. And I think with these examples, you should be good to apply to multiple coefficient of restitution. And next time we will be continuing this with different type of motion, which is the oblique motion, when these two bodies is not on the same line and they have velocities that has X and Y components. So Tony, do you have any questions on this concept?
None right now.
Okay. Do you have any other questions in the homeworks or anything?
Not at the moment. I need to keep working through it.
Okay, that sounds good. So that's all for now.
Okay, thanks.
All right. See you tomorrow.
See you tomorrow.